I thought I would give you two more examples of how you can use the RiseBox to solve these kind of questions. So I'm going to go through example 2 and 3, which are slightly different from example 1, but I strongly encourage you to try it for yourself before you watch this video. Okay, so let's look at example 2. You start with a system, so it's a reversible system, everything is a gas. And let's start by summarizing the question. So you have 0.25 mole of SO2, 0.25, and 0.35 mole of NO2. So NO2, 0.35. And then what happened to these? These are initial amounts and they are added to an evacuated 10-liter vessel. So evacuated just means there's no other gas present in the vessel, and clearly these are initial amounts. So I'm just going to put Ni here so that I know it's initial. When equilibrium is reached at 300 Celsius degree, the concentration of NO, so you're given concentration of NO at equilibrium. So NO equilibrium is 0.0224 molar. The unknown is the equilibrium constant of the reaction. So I need to find Kc, and I know that Kc, let's just write an expression for Kc. So it's SO3, the concentration of SO3 at equilibrium, multiply with the concentration of NO at equilibrium over SO2 times NO2. So this is an expression for Kc. So once I have the equilibrium concentration of all of these species, I should be able to calculate Kc. At the moment, the only equilibrium concentration that I have is of nitrogen oxide, so that's not enough. This is unfortunate. I should delete this. But basically, you see some information relating to the initial amount and some relating to equilibrium amount. So if you see initial and equilibrium amount in the question, that is indication that you probably want to use the RiseBox method. I do like the RiseBox methods, especially if you're not sure where things are going, because by the time you summarize information into the table, it becomes very clear where you need to go. So this is the RiseBox. We're going to use the RiseBox method for this question as well. So we're going to start with the RiseBox. Do I have anything? No. Okay. So now the other thing that I want to point out is the initial amount of the reactants are given in number of mole, but the product is the concentration. So you have to make sure that the units that you are using in the RiseBox is consistent. So what I'm going to do in this particular question is I am going to convert the initial number of moles of the two reactants to concentration before I begin. So the initial concentration of SO2, it's going to be, so just 0.25 divided by 10 liters, so 0.025 molar. This is the initial concentration of SO2, and the initial concentration of NO2 is going to be 0.035 mole, so mole per liter. So this is just a conversion from number of mole to concentration using the fact that the volume of the vessel is 10 liter, and that concentration is, so concentration, which is C, is number of mole divided by volume. All right, so we're going to fill that in. So we have 0.025 and 0.035. Now you can write the unit next to every number. I tend to just put like that. Do I have anything? I really don't have anything. And then I put 1 here. So this is just for me to know that the unit that I'm recording is mole per liter. So I have these are initial concentrations, and these are equilibrium concentrations. So 0.025, 0.035, and the NO equilibrium concentration is 0.0224. Okay, so 0.0224. Okay, now you also know that the initial concentration of the products must be 0, because the question indicates that you start with only the reactants in an evacuated vessel, so there shouldn't be any other gases present. And now all you need to do is to fill in the change column, or row, sorry. So if you start with 0 and end with 0.0224, you must have added 0.0224. So this is the amount that have been added to NO. This one's actually very easy because the mole ratio is just a 1 to 1 to 1 to 1. So you don't actually have to worry too much about mole ratio here. So if I have produced this much of NO, I have to produce the same amount in SO3. So also 0.0224, which means that you will have to subtract the same amount of NO2 and SO2. Okay, and then you just need to do the calculation. So 0 plus 0.0224 is just 0.0224. And I'm going to do the math here. So 0.025 take, so this is 0.0026, and then the next one is 0.0126. So now I have got the equilibrium concentrations of all of the species. I could calculate the equilibrium constant. So it's just, let's just write the expression once more. Just in case we screw up the number, we at least get that mark. So SO2 and NO2. So this means that you have 0.0224. Well, these two are the same, so you can square it if you want. But I'm just going to write it out. And then you have 0.0026 times 0.0126. You just need to be careful when you put this in the calculator, which I am doing right now. 0.026 times 0.0126. Okay, so I think we're looking at two significant figures. So 15 is the answer, and it shouldn't have a unit, so it's just 15. That is example 2. Let's move on to example 3. It's a little bit different. So let's just have a look at the question. So you have carbon monoxide reacts with steam to produce carbon dioxide and hydrogen gas according to this equation. So they already give you Kc in this case. So the first piece of information that you have is actually Kc. Now, when you're given Kc, what I tend to do is I would write the equilibrium expression. So CO2, H2, so product over reactant over CO and H2O. So this ratio equals to 810.5 at equilibrium. Okay, equal amount, so these two started off equal to each other. Equal amounts of CO and H2O are added to an evacuated vessel and allowed to come to equilibrium. So I don't actually know what the volume of the vessel is this time, and I also don't know the initial amount of CO and H2O. But I know that the concentrations of CO and H2O at equilibrium is this. So I know that concentration of CO at equilibrium equals the concentration of H2O at equilibrium, which is 0.0751 molar. And the question actually asks you to work out the initial concentration of CO, which would equal to the initial concentration of H2O, but I don't know what it is. Okay, very interesting. But once again, because there's some indications that you need to go from initial, in this case, you are going from equilibrium concentration back to initial concentrations, but since both of them are mentioned in the question, I would still use the rice box method. So this is my rice box. Did I even do anything? Actually, no, quite lazy. Didn't do anything. Okay, so you have CO and H2O. I feel like I should have picked equation that has a mole ratio that is not 1 to 1, but I guess we can do that when we do some practice questions later. So this gives you CO2 and H2. Okay, so we got the equation. What else do we have? We know that the equilibrium concentration is 0.0751. So I'm going to use concentration in my rice box. It doesn't matter whether you use number of mole or concentration. You just have to use the same amount. So 0.0751 for both of them. And you do know that your starting point, you don't have any products at the start. Okay. You don't know what these are and you have to find them. So my advice always, if you have an unknown, let's call it X. And I know that they are equal to each other at the start. So I'm just going to start with X and then X. So if you go from here to here, and it must have gone down because you start with 0 of the product. So you must have added some products as the system approaches equilibrium. So there must be plus sign on the product and there must be minus on the reactant. So all I need to do is to go from here to here. So the amount that you must have subtracted to go from x to 0.0751 is x minus 0.0751. Now, you can actually do this differently. I think I may actually do it differently. So I'm going to call x the change. I think that may make it a little bit easier for people to see. So sorry about that. I'm going to say that this one has to go up by x and that has to go up by x because it has to go up since the reaction has to go forward. And then that is going down by x and that is going down by x. And the reason why they all going up and down by the same amount is because the mole ratio, according to the equation, is a 1 to 1 to 1 to 1 ratio. So this ends with x, and the initial amount of CO and H2O will be 0.0751 plus x, and again 0.0751 plus x. Let's put it in a bracket just in case. Now that's everything I could do. I have one unknown, which is not bad. Things start to get tricky if you have two unknown, which shouldn't happen in chemistry. So if you run into that situation, maybe you haven't read the question carefully. The last thing that I haven't used is Kc. So I'm going to try to represent Kc in terms of x. So I have Kc equals to, so I'm going to write the expression one more time. So CO2 over times H2 over CO and H2O. So this is Kc. Now if we write it in terms of the equilibrium concentrations from this table, it's basically x squared over 0.0751 square. So x times x over 0.0751 times 0.0751, and it equals to 810.5. So from here, you should be able to solve for x. You probably want to do this calculation first, so you don't have to. So x is, let's just do it in one step, 810.5 times 0.0751 square, and then you take the square root of it. So x would equal to, I'm just going to put this in the calculator, 810.5 times 0.0751 square. So I have 2.138 or something, and you need to find what the question is asking, which is actually the initial concentration of CO and H2O, and that should equal to this number plus 0.0751, so 2.138 plus 0.0751. So I'm just gonna use the exact value and leave the final answer to 3 significant figures, so 2.21 molar. Let's put a box around it. So that's question 3. So again, I really do like the rice box method, but you don't necessarily have to use it. It does make life a little bit easier, especially when the question has mole ratio that's not 1 to 1 to 1 to 1, so you don't forget to consider the mole ratio. But that's it for this